Hello and welcome to my academy. So in this video, we are going to be looking at bending moment and shear force diagram for a uniformly varying load. And we're going to be considering this question on the board to explain this concept. So let's say we're asked to draw the bending moment and shear force diagram for this given uniformly varying load. All right, so the first thing to do, is to start by drawing your free body diagram. Okay, so you simply put down your beam structure. Now, I have a pin support here. I've explained this in the first video. For the pin support, I simply say we have two reactions, one vertical and one horizontal at point A, where the pin is occurring. So we have a vertical reaction here. So you simply call this RAY. You have a horizontal reaction there. You call that RAX. So that's point A. Then at point B, we have a roller support. Now, these circles here, or those balls there, simply means that support is a roller support. And for a roller support, I also explained that in the first video, that for a roller support, we simply have one reaction which is normal to the surface or simply perpendicular to the surface. And in this case, since this beam is a horizontal beam, it simply means that that reaction is going to be a vertical reaction. But if the beam was to be a vertical beam, then the roller support there will not have or produce a horizontal reaction. Okay, so at point B, we simply have a vertical reaction. Okay, because the because the support there is simply a roller, so we have this to be RBY. Now this load is uniformly varying load, gradually increasing from 0 to the maximum, and the maximum value there is simply 50 kilonewtons. Now I explained in the first video that involves uniformly varying load that the first thing you have to do is to convert this load to a point load. Now to convert a uniformly varying load to a point load, you simply take the area of the shape. Since this shape is triangular, it simply means that your point load becomes half base times height, where the base is simply the length covered by the uniformly varying load and the height is the maximum load occupied by the uniformly varying load. And in this case, our maximum height is simply 50 kilonewtons per meter. So this means now that the point load is going to be equal to 1 all over 2 multiply the base is the length occupied by the UVL, in this case 4 meters. So multiply by 4 meters, multiply by the maximum load is 50 kilonewtons per meter. So 50 kilonewtons per meter. So if you observe, this meters cancels this meters, therefore the load now becomes half times 4 is 2. 2 times 50 kilonewtons is simply 100 kilonewtons. So you have your load to be 100 kilonewtons. So this becomes our point load. Now this point load has to be placed on the beam at a distance 2/3 from the tip of the UVL, or from the tip of the uniformly varying load, or 1/3 of the length from the base of the uniformly varying load. So any one you choose, you're always going to arrive at the same result. Now we want to place this point load. You simply place this point load at 2 all over 3 of the length occupied by the UVL from the tip of the UVL. So this is going to be equal to 2 all over 3. The length occupied by the uniformly varying load is simply 4. So multiply by 4. This gives us 2 times 4 is 8. 8 divided by 3 simply gives us approximately 2.7 meters. So this simply means that if you measure from point A, you simply measure at 2.7 out of 4 meters. Whatever is left simply becomes 1/3 of the length from the base of the UVL. Okay, so if you measure out 2.7 from 4 meters, it means you're left with 1.3 meters. So that means this load can be found somewhere around here. This load can be found somewhere around here. This is the value, 100 kilonewtons. And the distance from point A to this point where the load is found is simply 2.7 meters. This simply means that the remaining distance of this load becomes what? 1.3 meters. And if you add them up together, you still have the entire length of the beam. So we have to place this point load can either be 1/3 of the length from the base, and if you measure 1 all over 3 of the length is 4, it's still going to be, this is 4 all over 3, and this will still give us 1.3 meters approximately. So even if you're measuring from the base, you will see arrive at this point, 1.3 meters, where this particular load now is found. So it's either 1/3 from the base or 2 all over 3 of the length from the tip. Now, having achieved this, your next target is to what? Simply find your reactions. And I explained in the first video that there are two methods in which you can find these support reactions. You can either use the moment-to-moment method, where you simply take moment about the unknowns. So if I want to find RBY, I will simply take moment about point A. And if I do that, the moment of these two forces automatically becomes 0. That will help me to find RBY. Or if I want to find RAY, I simply take moment at point B. If I do that, I can now simply find RAY. And the moment of RBY about that point simply becomes 0. That is the moment approach. I use that to achieve the same result. Else, if I want to use the alternate method, which is a combination of the equilibrium equation, the equilibrium moment equation, and the equilibrium force equation. So I have to consider the equilibrium equation of the forces and then the moment and combine the equation to achieve the same result. Whichever you choose, you're going to arrive at the same result. But in this video, I'm simply going to maintain the moment-to-moment approach for this video because it is shorter and it is better off to use. Now, I want to find RAY. I will simply take moment at point B. If I do that now, mind you, you can simply call here point C. Since it wasn't indicated in diagram, you can simply call that point C. So let's take moment at point B. Moment, summation of moment at point B is going to be equal to 0. Let's consider clockwise moment to be positive and anti-clockwise moment to have a negative moment. Okay, so if we do that, we are simply taking moment at point B. Now, this force RAS lies on the same plane as the plane of moment. When a force lies on the same plane as the plane of moment, the moment of that force becomes 0 because moment is supposed to be the product of the line of action of a force to the perpendicular distance that force makes with the point of moment. So this force is supposed to act at 90 degrees to the point of moment, but this force is lying on the same plane as the point of moment. So the moment of RAS about that point automatically becomes 0. But RAY is pointing upward, so this is actually at 90 degrees to the point of moment. Now, this force is pointing upward, which means this force will turn about in this direction to take moment at point B. And this direction, from what we assume, is a clockwise direction. We said let clockwise moment be what? Positive. So the moment of RAY about point B is going to be positive. Total distance it takes RAY to get to point B is simply 4 meters. 2.7 plus 1.3. That gives us 4 meters. So it means that the moment of this force, RAY, okay, times 4. That gives us the moment of that force. Now we have another force here, 100 kilonewtons force pointing downwards. This force will turn in this direction to take moment at point B, right? Because it is acting downwards. So it turns about in this direction. And this direction is what? Anti-clockwise direction. And we said let anti-clockwise moment be negative. So it means the moment of that force automatically becomes negative. Now, total distance it takes this force to get to point B is simply 1.3 meters. So you simply have 100 multiplies 1.3. And the whole of this is going to be what? Equal to 0 from the moment equation. So RAY times 4 gives us 4 RAY minus 1.3 times 100 gives us simply 130, and this is going to be equal to 0. So you can simply send negative 130 over here. This simply implies that 4 RAY is equal to 130. So we can now make RAY subject. RAY becomes 130 divided by 4, which simply implies that the reaction at point A is going to be approximately 32.5 kilonewtons. So we have found the value of the reaction at point A, 32.5 kilonewtons. Having found this, you apply the next moment. Now you're taking moment at point A. Since you already know the value of RAY, you simply take moment at point A to find the value of RBY. Okay, so our next target is now to take moment at point A. So we simply take moment, summation of moments at A is going to be equal to 0. Let's also consider clockwise moment to be positive, anti-clockwise moment to be negative. So if you do that, once you take moment at point A, the moment of these two forces about point A automatically becomes 0, simply because these two forces have no distance to point A. They already exist at point A. So their moment about point A equals 0. Same thing happens to the moment of this RBY about point B. So with that now, we have to now take the moment of these other two forces about point A. Now, you have a 100 kilonewtons force acting downwards. Moment of this force about point A will simply turn in this direction. So if it turns in this direction is what? Clockwise. We say let clockwise be positive. and this direction is clockwise. So the moment of this force is going to be positive about point A. Total distance it takes this force to get to point A is 2.7 meters. So the moment of that force becomes 100 multiplies 2.7. Now you have arrow by pointing upwards, which means this moment will turn, or this force will turn about in this direction to take moment at point A. And this direction is simply anti-clockwise to our assumed direction. And we said anti-clockwise moment should be considered negative. Total distance it takes this force to get to point A is its total length of the beam, which is 1.3 plus 2.7, and that gives us what? 4 meters. So the moment of that force becomes negative or minus RBY multiplied by 4, and this is going to be equal to 0. So 100 times 2.7 gives us 270 minus 4 RBY equals 0. So from here you can have that 270 is equal to 4 RBY, and therefore RBY becomes 270 divided by 4, which implies that the reaction at point B is going to be equal to, this should give us approximately 67.5 kilonewtons. So that becomes the reactions. Okay, having found the values of the reactions now, our next target is now to carry out our shear force and bending moment analysis. And then we'll head on to plot the diagrams. Alright guys, so having obtained your reactions, you simply fall back to the original diagram and not the free body diagram. The free body diagram was just to aid us find the reactions. But in this kind of situations where you have a strange type of loading which is not a point load, then you simply fall back towards the original diagram and plug in your reactions. So we start our shear force analysis. Shear force analysis. Okay. Shear force analysis. So the shear force at A is simply the force that exists at point A. And when doing your shear force analysis, always consider vertically upward force to be positive and downward force to be negative. At point A, the force there is 32.5 kilonewtons and it is pointing upward. So you consider it simply as positive. So shear force at A is simply 32.5 kilonewtons. Also keeping it in mind that at the end of every shear force analysis, you must always have 0 as your result. So if you don't have 0 in this situation, it means we are wrong. Now, there is no other point on this beam apart from point B. But moving from point A to point B, you observe that there is a different type of loading that is here. This loading is simply a uniformly varying load. For that reason, you have to form what is called the shear force equation. Now, the shear force equation helps us to know the kind of diagram we are going to be drawing for our uniformly varying load. It also helps us to determine the point of maximum bending moment. That's what the shear force equation does for us. Okay, so we have to take a section. You have to consider a section at any point along AB or along where this uniformly varying load is found. You simply take a section from beginning of the beam. So you simply consider a section XX. You make a short note. Consider a section XX. Okay. Consider a section. Consider a section XX at a distance X from A along AB. So you simply consider a section, and that section is at a distance X meters along AB. So you can simply fall somewhere around here and you make your section just somewhere around. You can make your section here. This is your section XX, and you're simply saying that the distance from point A to the point of section is now going to be what? X meters. That becomes your, that's your condition now. So what you need to do now is find the shear force of the UVL about the point of the section. Find the shear force of the uniformly varying load about the point of the section. So you start, shear force AB is going to be equal to, so you remember it was this previous shear force 32.5 kilonewtons that encountered this strange loading on the beam, right? So you recall the 32.5 kilonewtons force. Now we have to convert this uniformly varying load to what? A point load, considering the section. And we said to convert a UVA to a point load, you have to take the area of the shape. And what is the area of a triangle? The shape is triangular. Area of a triangle remains half base times height. In this case now, the base becomes the section length, or the length about the section. That becomes the base, not the original length, the length about the section, which is simply x here. The height remains the maximum load of a uniformly varying load, which is 50 kilonewtons per meter. So therefore, and since these loads are acting downwards, it means that it's going to be what? A negative force. So the shear force equation becomes minus half base is simply x, half times, okay, half times base is x times height remains 50. This becomes our shear force equation. So if you evaluate this, shear force along AB is going to be equal to, this is 32.5, half times 50 gives us 25, so you have minus 25x. Now this equation is simply our shear force equation, and if you equate this equation to 0, you find the point of maximum bending moment. Now I will do this at the end of the video, so I'm going to explain the point of maximum bending moment and the point of contraflexion and how you can get them. Okay, so now this is now along AB, but our idea is to find the shear force equation, or to find the shear force at point B. So you now simply consider at B. At B, remember, X now becomes total length of the beam. So at B, remember, X started from A to this point and we called it X. Now, if X extends finally to point B, it means it becomes the entire length of the beam, which is 4 meters. So it means that at point B, our distance X becomes 4 meters. Now, this will help us to find shear force at point B. But you have to consider that at point B, we already have a force there. And since we have a force there, then you have to now make a short note. This is now going to be at B prime, which means initially at point B, the shear force becomes, okay, so initially at point B, you simply say shear force B prime, which indicates initially at point B, your shear force now becomes 32.5 minus 25x. X there is 4 now, so this is going to be equal to, so I will simply evaluate everything together. 32.5, 25 times 4 is 100, so 32.5 minus 100 simply gives us negative 67.5 kilonewton. So shear force B prime, which means initially at point B, the shear force is simply negative 67.5 kilonewtons. Now, finally at point B, you indicate that with shear force B prime prime, which means finally at point B, this negative 67.5 kilonewtons force now encounters an upward force of value 67.5, and since it's upwards, it's considered positive. So negative 67.5 plus 67.5, and this simply gives us 0. So at the end of every shear force analysis, you must always have 0 as your answer. So this is achieved. We have 0 now. Next, we move to the bending moment analysis. Bending moment analysis. Okay. Now, for the bending moment analysis, you start as well from beginning. From equilibrium equation or from equilibrium law, the moment of a force about any point is always 0. So the moment of this force, 32.5, about point A, is considered to be 0. So moment at point A is simply 0. Bending moment at A equals 0. Now, since moving from point A, we encounter a strange type of loading, you also make this same note, but I'm not going to be stating it now since I've already stated it there, but we also make this same note. Consider a section XS at X from A along AB. So we've considered the section already. Distance about the section is simply X. We want to find the moment about the point of section. And you know that moment is simply force times distance. That means I have to consider the moment of this force, 32.5, about the point of section. Remember, moment is force times distance. Therefore, total distance it takes 32.5 kilonewtons force to get to the point of section still remains what? X meters. So the moment of this force about that point, first of all, this becomes bending moment along AB. So you have bending moment along AB. That becomes you have 32.5 multiplied by x. That becomes the moment of this force, 32.5 kilonewtons force about the point of section. Next, we have a uniformly varying load also about the point of section. So we have to take the moment of that load about the point of section. Now, the idea now is to form what is called the moment equation. With the help of the moment equation, we can be able to find the point of contraflation. And the moment equation also tells us the nature of the diagram of the bending moment itself. Okay, so you have to first of all convert, remember, you have to first of all convert the uniformly varying load to point load first. When you get the point load, then you now take the moment of this point load about the point of section. So we already established this earlier. This is the point load, and this is going to be equal to half base is x times height is the maximum load. So this actually gives us 25x. This is the point load of the uniformly varying load, also gotten in the shear force analysis here. So this is now the point load, but we want to take moment. So you consider this now. This is the, let's draw out this diagram just to explain. So this is the point of section, right? This is our point of section xx. This is our distance x. So this is the uniformly varying load. Okay, just to explain better. Now, if I've gotten my load, this is now the beam that contains the point of section. From here to this point is x. If I've gotten my load, we explained earlier that after obtaining this load, the next thing you do is to place this load at 1 2/3 from the tip of the UVL. You place this load at 2/3 of the length from the tip of the uniformly varying load. And this is the tip of the uniformly varying load, which can be simply said from here. So 2/3 of the length. The length now becomes the length of the section. In this case, is x. 2/3 is simply somewhere around there. So that means distance from here to this point, is simply 2/3 of the length x. Therefore, the remaining distance about the point of section is simply what? 1/3 of what? The length x. So which means the moment of this force now is simply 25x, which is the force of the uniformly varying load about the point of section. Therefore, the moment of this 25x about the point of section simply becomes what? 25x times total distance it takes the force to get to the point of section. In this case, is what? 1/3 of what? X. So times 1/3 x. This becomes the moment of the force about the point of section. So it's a very simple concept. Therefore, the moment becomes now minus, because it's acting downwards. You have the point load. Okay, 1/2. The load itself is 1/2 times distance x times maximum load is 50. Now multiply by distance it takes this force to get to the point of section, and that is what? 1/3 of what? The length x. So you simply have 1/3 of x. So this is going to be equal to 32.5x minus, this is already explained, half times 50 is 25 times x is 25x. Now 25x multiplied by 1/3x. X times x is x squared. 25 divided by 3 gives us approximately 8.3x squared. So this is our bending moment equation. And you can see that this is parabolic in nature. That means the diagram of the bending moment diagram is going to be what? A parabola. Okay. Now, also have it in mind that if you equate the bending moment equation to 0, the value of x you obtain here simply tells us the point of contraflation. Just like we said in the first case, if you equate the shear force equation to 0, the value of x you obtain is the point of maximum bending moment. And it tells you the point where shear force changes sign from positive to negative. That is where the maximum bending moment occurs. Whereas the point of contraflation is simply when you equate this bending moment equation to 0, the value of x you obtain there is simply called the point of contraflation. Okay, so let's go on now. We are done with this. The next thing is to take moment. Our target actually is to take moment at point B. That's our target. We need to find the moment of the force at point A. We've gotten at point A. We need to now move at point B. So you now consider that at point B, just like we said earlier, at B, x is equal to 4. Okay, so at point B, x equals 4. Therefore, you can now find bending moment at point B. And this is going to be equal to, that means anywhere you see x, you put in the value as 4 in this equation. So this gives us 32.5 multiplied by 4 minus 8.3 multiplied 4 squared. This is going to be equal to, let's obtain 32.5 multiplied by 4. That simply gives us 130. So we have 130 minus 8.3 times 4 squared. All right, so 8.3 multiplied by 4 squared gives us approximately 132 point 6. Okay, so just so you know, this is supposed to actually be 130, but due to approximations that we've done as a result of the calculations, that is why we're having 132.6, right? It's just due to approximation. So you should have 130 minus 130. Now, the approximation stems from the reactions force. We approximated it to 32.5 and the other one to 67.5. So these are all approximations that we did. Even from here, we said 25 divided by 3, we said 8.3. So it's just as a result of approximation. So we are completely not far from the result, right? So 130 minus 132.5, we are going to be assuming this to be 0 because at the end of every bending moment equation, which analysis, we should have 0 as the result. So 130 minus 132.6 is not far from 0, right? All I'm simply saying is this is supposed to be 130 on the dot, but due to approximation that we've done earlier in the calculation, that is what is affecting this result here. So our moment equation should actually be what? Equivalent to 0. So just keep this in mind that our moment equation is simply supposed to be 0 at the end of the beam, right? Okay, so we are done with the shear force analysis. We are done with the bending moment analysis. We simply move on now to what? Plot the diagram. Okay. All right, so in order to plot the diagrams, you trace out these 2 points. Point A, trace it out. You trace out point B, trace it out. So we'll plot the 2 diagrams via freehand sketch. So let's start with the shear force diagram. You draw a horizontal line here. So this is the origin, 0. Okay. So you picked out the shear force values. Shear force at A, 32.5. And that seems to be the highest value of shear force that we have. So here, you can keep it here, 32.5 kilonewtons. That's the shear force at point A. Then we have shear force at B prime, negative 67.5. So negative 67.5 can be here. So you have negative 67.5 kilonewtons. Okay, and then finally 0. Okay, so let's trace out all the points. Trace out all the points. You also trace out these points. Okay, now let's draw the shear force diagram. Shear force at point A is 32.5 kilonewtons. This is point A. This is 32.5 kilonewtons. This is where they meet. You simply asterisk. You simply asterisk. Okay. Shear force at point B initially. B prime is negative 67.5. This is negative 67.5. This is B. So you simply asterisk where they meet. You asterisk. Finally, shear force at B prime prime, which is final at point B, is 0. This is B, this is 0 mark. You simply asterisk where they meet. Okay, so you have this. Now we need to plot this diagram. All right, so in order to accurately draw our shear force diagram, let us first of all find the point of maximum bending moment using this equation, right? The shear force equation. So we simply equate this to 0. Equate this to 0 and let's find the point of maximum bending moment, which is simply x. So if you do this, you're going to have okay, you're simply going to have, let me segregate here. So you're going to have 32.5 to be equal to 25x. If you simply say negative 25x over here, it becomes positive, right? So therefore x becomes 32.5 divided by 25. So let's see what this gives us. So whatever value of x you have here simply tells you the point of maximum bending moment. So you have 32.5 divided 25. That simply gives us 1.3. So this means that x is equal to 1.3. So 1.3 meters is the point where shear force changes sign from positive to negative. The point where shear force changes sign from positive to negative is simply the point of maximum bending moment. And the value is simply 1.3. So you simply measure out 1.3 from 4. If you measure out 1.3 from 4, that should be somewhere around, okay, we can simply call that, remember we're using a freehand sketch, so we're not entirely accurate. So the remaining remains 2.7 meters. So this is the point where shear force changes sign from positive to negative, which indicates the point of maximum bending moment. Okay, so this is the point of maximum bending moment. So let's draw our shear force diagram now. Once again, the shear force equation is simply linear in shape, so which means our graph is going to also look like a linear graph, right, in shape. But then before doing that, RAY indicates a point load, value is 32.5. So you simply from the origin draw the shear force diagram for a point load is simply a straight line that connects each of the points. So you simply connect here with a straight line. Okay. Okay, so we have this. Now we want to draw the shear force diagram for the uniformly varying load. It's linear in shape. So you're going to be having something like, and it has to pass through 1.3 meters. So you have something like this, passing through 1.3 meters to point B initially. Okay, and then finally, RBY is also a point load. Shear force diagram for a point load is simply a straight line that connects each of the points. So you have something like this. So this becomes our shear force diagram. So you can choose to shade. Okay. So this is positive and this is negative. This is positive. This is negative. So this is where the shear force changes sign from positive to negative. Distance is simply at 1.3. Okay. Next is to draw the bending moment diagram. So you simply okay, let's trace this down. Trace this down. So you draw another origin. So this is the origin line 0. So our bending moment values, okay, is still 0, 0. Moment at point A is 0. Bending moment at point B is also 0. So simply, moment at point A is 0. Moment at point B is also 0. So you simply plot your graph. Now, since this is the point of maximum bending moment, that means bending moment should be maximum about this point. So your diagram will simply, now the bending moment diagram for a uniformly varying load is simply a curve. And you can see from the equation, it's parabolic. So we are simply going to be having a curve, right? So you simply draw a curve, which is maximum at the point of maximum bending moment. And then you have this. So this is our bending moment diagram. So you can simply shade. Okay. So this is the shear force diagram. And this is the bending moment diagram. So that's how you draw the shear force and bending moment diagram for a uniformly varying load. Once again, we've also explained the point of maximum bending moment. Just in case you're asked to find the point of contraflexure, simply equate this to what? 0. Find the value of x here. The value of x you obtain here is simply the point of contraflexure. All right, guys, so that's it for this video. I'm sure you find the video very interesting and helpful. Please, if you do, I would like you to leave a like, comment nicely, share to your friends, and if you're new to the channel, do well to tap the subscribe button right now and turn on your bell notification so you don't miss out on our subsequent videos when it drops. I will see you in the next video. Thanks.